Now, I want to have your attention for tonight. We will tell you all about how big you can hack a very small machine. Thank you for your attention.
Welcome to this talk about cracking the PSP. Very little bit of background about me. I've been developing on the PSP non-officially for about 3 years now, so it's about the length of the time of the console. And I'm the developer of some of the main dev tools which people use on the PSP. But I was also a member of the Prometheus project, better known as Team C&D, which produced a lot of exploits and in the end produced the ultimate exploit for the PlayStation Portable. And I have to thank all the people which have, over the years, contributed towards breaking Sony's little device. In particular, mention the Prometheus team themselves, and you can't not clap for Sony because obviously they produced the system in the first place to be so exploitable. So, this is an overview of what I'm going to talk about. I'm going to start with a basic overview of the PSP security model, how it should have worked or how it should work. Then I'm going to talk about the breaking of the original Japanese firmware, which was instrumental in progressing the sort of PSP hacking and cracking scene. And finally, I'm going to talk about service mode and the creation of Pandora. Pandora is as I said, the ultimate sort of hack for the PSP, and basically allows you to run code, arbitrary code, on any current PSP hardware model. So, PSP was arguably designed to be secure. Sony didn't really want it to be an open platform. They didn't want unauthorized software from running, either pirated software or homebrew, because sometimes they tend to believe they're one and the same. And they did this through two sort of distinct areas of their security. They had boot time and hardware security, and they had runtime security. Now the boot time, probably should be fairly obvious, is there to protect the boot process. They knew they wanted their operating system to be flash upgradable, so they can fix bugs, they can add features. So, as that is slightly a bit of a hole, if someone can overwrite the flash with their own code, they decided to implement a chain of trust, and they utilized their built-in hardware security engine, which is referred to as Kirk. Now, before anyone asks, Kirk is actually a reference to Star Trek. There's various other names in the hardware, and on the dev kit there is apparently even Spock. So the chain of trust goes basically like this. Inside the CPU, sort of on a mask ROM, we have a little bit of boot code, or what we refer to as the pre-IPL, IPL being initial program loader. And you've also got Kirk sitting on the same CPU. The pre-IPL's job is to basically load, decrypt, and verify the IPL stored in the flash ROM. And it uses Kirk to do that. The IPL then can load and verify system and local, again using the Kirk hardware engine. And finally, the main kernel is brought up. Now on runtime security, it's fairly obvious, becomes important once the system is initialized, otherwise it wouldn't be runtime. And the firmware, the PSP OS is not actually a sort of general purpose operating system where it tracks all your resources and can clean up after you. So in order to switch between, say, the main Sony menu and a game, it literally resets itself. Now, it doesn't go back to the initial pre-IPL to do this, so it's just a circular chain of trust in that it's trusting you've already booted securely, and then when you reset, it resets securely, which is obviously a bit of a fallacy. And they also restrict what type of files can be loaded. So they restrict where you can load executables from. Say, you can't load them from a memory stick in this this state, but you can load them from UMD, which is the Universal Media Disk, which is their optical drive. And executables can be encrypted and verified by Sony. And even if you do get user access to the system, there is a kernel and user separation. So you can't do much in user mode. And you would have to actually attack the kernel itself to get full runtime. They didn't, of course, stop there. Save games seem to be the bane of console manufacturers' lives. So they encrypted them using, again, the onboard hardware. This makes it quite difficult to reproduce without access to the PSP getting code to run the PSP itself. Update files are encrypted and checked again, and there's no user-accessible process to downgrade the firmware. So once a firmware is on there, you can't put anything with a lower revision back on directly. And to prevent you from just copying the flash from one PSP to another, they do some data encrypted on a per PSP basis. Now, Sony weren't completely stupid. They thought, well, we might have reasons to run software from the memory stick. For example, demos, and in this case, the updaters. And to do this, they packaged an executable in a nice metadata format, which some might recognize with eboot.pbp file name. And putting it out on the memory stick, it should run it. But the executable had to be encrypted, otherwise it shouldn't touch it at all. So that's what it would be on paper. It seems reasonably secure. There's obvious flaws. If you gain execution, you can subvert the reboot process and things like that, but it's getting code on there in the first place, and they can fix bugs with the firmware updates. Now, this is how not to implement that security. The PSP came out in Japan around the 12th of December 2004. So it's been over 3 years now. It came with version 1.0 of the firmware, and it's probably fairly certain it was brought forward to try and steal a bit of Nintendo's thunder, with the NDS being released on December 2nd. So, of course, people got to work. That is an example of a modification to basically read and write the flash chip on board. A lot of work on that. This is produced by Nem, who is with us today. But the hardware hack gave us information, but it didn't directly lead to something to execute until someone sort of posted on the PSP dev forums. At this point, the US PSP had been released, 1.5 firmware had been released, so you could now get an updater for it. And you had your eboot PBP, which is all your metadata. So someone came up with the idea of replacing the encrypted executable with a simple ELF file, which I think this person had probably originally got from the development kit. And surprise, surprise, running it, it actually started, and it worked. And obviously, you've got to have a hello world, so that was the proof that, yes, you could actually run completely unencrypted, unsigned code on the PSP. But that still only gave us user mode. And as I've said before, kernel mode is where the real action is. It's where all the hardware is set. So we really wanted kernel mode. Now, how were we going to get in there? We could either exploit the kernel, but we didn't know how it worked. We didn't have any unencrypted versions of the kernel. Or we could try and encrypt an executable ourselves, but that's even less likely to be possible. So after a bit of playing around, we worked out how to do it. And basically, you ask, if you say you're a kernel module, it will load it. Slight flaw in that. So sort of, what the fuck on that? It seemed version 1 had two types of executables which you would recognize. Had standard, pretty much vanilla MIPS ELF files, and it had these modified relocatable ELFs PRX files, possibly PlayStation relocatable executables. Now, all the games, the firmware, etc., use these PRX files, but it seems that Standard Elf was left in accidentally from development purposes, and they kind of forgot to add the protection check for that format. Interestingly, the PRXs must be encrypted to load off memory stick and must be encrypted to act in kernel mode. So they basically wrote in their own backdoor. I'm not sure how well we can see that, but basically the speculation is, this is a list of the loadable modules from the version 1 firmware. And as you can see, a couple of lines what look to be commented out. And the one at the bottom is called Decky2p.prx, and Decky2 is Sony's communication protocol for their debuggers. So it looks awfully like version 1 was a debug firmware, and they just commented out a few modules. So it's no wonder that there was a big hole in it. So that was the end of version 1. Sony kept trying and trying. But virtually every revision of their firmware has had one flaw or another. Probably the most amusing one is the race condition bug in 1.5, where swapping a memory card between pressing a button and when it actually boots would actually allow you to swap in an executable and run it. That wasn't particularly convenient for people until someone found that by putting a % on one of the directories, so you have two directories named almost the same, one with a % sign, the menu would read the one with the % sign, and by the time it got to the other side, the % sign had gone, and it ran the executable for you. We had third-party library exploits. They got hit by libtiff exploits twice. Save game buffer overflows. Because we now had code running on the system, the save game encryption was completely useless. And they sometimes forgot to check their parameters correctly in the kernel, which allowed us to basically elevate privileges into the kernel. Right, so let's talk about the ultimate hack, Pandora. Sony left in a service mode into all PSPs. This was ostensibly for they could flash them in the factory without actually having to open them up and solder stuff onto the board. And you could fix a bad flash. If you send it back to service, they could boot it up and fix the flash for you. And based on leaks from various people, this seemed to consist of a special battery you inserted and a memory stick. But by this point, the IPL would be reasonably well reversed, and nothing was obvious in there it was doing any sort of recovery mode. And as that's stored in Flash, it would be kind of useless to stick it in the IPL. So, speculatively, it's probably in the pre-IPL. Unfortunately, the PSP's IPL disables the pre-IPL before we even get close to it. So, how the hell are we going to get hold of it? So now into techie bits. This is what an encrypted IPL block looks like. Some bits are a bit unknown, doesn't really matter. We've got encryption key, we've got two 16-byte hashes in there. We've got size, various sizes, and then we've got our encrypted data. When that's passed to Kirk, what we get back out is this. We've got a 16-byte header, which contains the load address where we need that block to be in memory, the size of it, the entry point, which acts both as a marker for the end of a list of IPL blocks and the point where we want to jump. So if it's not 0, it will actually jump to that address. And we have the previous data block to checksum. This is just a simple 32-bit summation over the entire unencrypted data. And this is then set up in chains in memory. So it reads block 0, decrypts it, and because it's the first block and has no previous block, its checksum is 0, or set to 0. The pre-IPL will then load block 1, validate the checksum's correct, and it will keep repeating that until it reaches a block which has the entry point set, and then it will jump to it. So this, because we can't affect the unencrypted versions of these blocks, this should prevent you from sort of modifying the order of the blocks. Unfortunately, they set the first one, there were 0 checksum. And they were stupid enough to not realize that other blocks in the IPL had a 0 checksum. So it was possible to remove a few blocks out of this chain and create a large memory hole. Basically like this. We have block 0, block 1 has an actual checksum of its own checksum of 0, and therefore we can cut out block 0 and 1, which leaves a large uninitialized memory hole in the boot process. So if we can get custom code into there somehow, we can gain execution at the IPL time and dump the pre-IPL. So how are we going to get data into that area of memory? Well, RAM wasn't cleared on a power cycle. This wouldn't necessarily be a problem. But using a mod chip, it's trivial to have 2 different firmwares set up, which you can easily switch between by holding a button down when you power up. So you boot one of the firmwares and fill in this memory hole with your own exploit code. You can then power cycle, hold down your button. This will now boot the IPL, which has a large memory hole in it, and it will end up jumping straight into our code. And from there, you can dump the pre-IPL, you have full control over the system. It's not a very practical exploit for the purposes of gaining runtime, which it is effectively doing, but it is certainly useful for dumping the supposedly hidden mask ROM. And yes, it's amazing Sony didn't sort of realize that this was going to be a problem, but I suppose you can't really blame them. They perhaps just assumed you couldn't fill that memory with anything useful at all and actually gain execution. Step 2, trying to find the battery. The pre-IPL, as you might expect for a sort of mass ROM inside a CPU, is not particularly massive. It's about 4K or so. So it's fairly easy to reverse. And based on this reversing, we found a jump halfway through the code, which basically said, if this bit is set to 1 in the hardware, jump to flash. If it's not, well, read from flash. If not, read from the memory stick. And this tied in perfectly with the information we have that we needed some sort of memory stick to enable service mode. So then it became a case of trying to find how to enable that pin, and probably it was something to do with the battery. So we tried various things and trying to see how to enable service mode. And it turned out the PSP battery contains a very small ROM, which you can just access over a serial bus. And it includes information such as a serial number. Seems fair enough, has a serial number. But it seemed that setting the serial number to all Fs would automatically start the PSP and enable service mode for you. Don't know why. It seems fairly simple, but that's how they implemented it. But batteries are a piece of hardware. Software engineers don't like hardware. Is there another way we could have done it? Well, fortunately, most of the batteries on sale stored their serial number in an E-squared PROM. And it just so happened that the kernel provided functions to change that very serial number. Yes, so that worked quite well. Right, this is sort of the final sort of bit of the presentation. It's quite a quick presentation, it seems. Service mode is possible. We know that now. We know where it jumps to. Well, we know where it reads off the memory stick. Now, obviously Sony have memory sticks which can be bootable and do something like flash the ROM with a certain version of the firmware. But that would be illegal to get hold of. It hadn't been leaked, so we had to create our own. So how are we going to do this? The pre-IPL is encrypted. It's hashed with what doesn't look to be a standard sort of hash. It's probably sort of message authenticated. which is probably providing the sort of signature protection. And we want our IPL code to load without any hardware modifications at all. So the barrier to creation of this IPL code, we've got our 2 hashes, which are 16 bytes each, and we also need to create some encrypted data. Now, it was noted that Kirk, which is our security engine, had a couple of side-channel timing attacks in it. It seemed that when it calculated the hash, certain hash, it calculated it before and then checked it 32 bits at a time. If any of those 32 bits fail to validate, they weren't correct, it would exit immediately. So you had basically a simple timing attack where you could brute force the first 32-bit word. Once that's correct, you can brute force the second, and so on. This obviously breaks down our 2 to the power 128 searches, which is sort of in eon sort of time frames, into 4 of 2 to the 32, which then becomes sort of in the days rather than the millions of years. So that gives us our data hashes. So we can create a valid IPL block. We can fill it with garbage encrypted data and hope it decrypts to something useful. But as shown on the slide where it showed the decrypted block, we have a 16-byte header, and potentially we need at least 8 bytes of code to do something useful. So that would amount to 24 bytes, which is even more of a brute force search than our 2 to the power 128. So what can we do to reduce that number? Fortunately, Sony kind of slipped up again. And the pre-IPL and Kirk had basically 4 issues which made this possible to do. Firstly, it always loaded 4K. Doesn't matter how much it decrypted, it will always load 4K into memory. Each block is decrypted in place. So the input address and the output address of the IPL block was exactly the same. They didn't bother to check how many bytes they actually wanted. So if you've only got 4 bytes decrypted, it will still assume you have 16 bytes valid header data. And the pre-IPL will basically jump to an arbitrary point. It doesn't matter that it's not in where it's loaded the IPL, it doesn't care. So normally, you would load an encrypted block from memory into this static buffer, which we knew where the address was because it was in the pre-IPL. It gets thrown to Kirk, and we get a decrypted block. But you can see there's a small red bit underneath, which is actually the remnants of your encrypted block. Then it tries to just copy the decrypted block into RAM, where it would normally try and execute it. So, through a bit of testing, found that smallest decryption you can do is 4 bytes. Now 4 bytes is slightly easier to brute force than 24 bytes. So, with a bit of work, a decryption was brute force, which basically wrote 4 0 bytes, which is very useful. As the decryption is in place, these 4 bytes get written to the start of a loaded block and leaves 4,092 bytes of completely untouched data. So as the decrypt area is static, all we have to do then is set the entry point into that buffer, and it will jump to it. So that was the encrypted IPL block. This is one filled in with a few values, a few useful values. The key is set to mostly zeros, except there's obviously a few interesting bytes towards the end. We have our header and data hashes set. We have 4 bytes of decryption, and we have our brute forced encrypted values. And at the bottom, we in effect have from 256 up to 4K boundary, we have completely unvalidated data which is sitting around. So we throw that to Kirk, and yeah, it writes the first 4 bytes back out. It was 0 to begin with, it's now still 0. And because we now have no block size, it doesn't copy anything. And our entry point is set. fortunately, to an address smack bang into the middle of our decryption buffer. At this point, the pre-IPL goes, okay, that's the end of my IPL. I don't need to go anymore. Let's just jump to that address and be done with it. So it does. And there we go. It completely breaks the PSP security model, what security model it had. And when combined with a service mode battery, we could create an IPL on the memory stick, which would allow you code execution on any arbitrary PSP hardware. Doesn't matter what revision it is. Even works on the very latest slim and light models. Although unfortunately, our code didn't have video code, so it tends to be rather dark when you're trying to do it. They tried very hard, and they keep trying. But in the end, both hardware and software tripped them up. There's not much they could have done about it, really. And once that initial version 1 break was enacted, we could see all their secrets. It was pretty much security through obscurity all along. But I think the PSP is better for it. It's quite a nice little console to program on. So, that's quite a short presentation. Any questions? Yeah.
Hello? Oh, yes, hello. Now that you do have kernel mode, do you know anything about the hardware itself? I mean, do you know how the graphics chip works, for example? Can you do fun stuff with the machine?
Yeah, we know an awful lot about the hardware now. People have finally got sort of micro C Linux running on it, which requires a fair amount of hardware knowledge. We can pretty much do any graphical work. The kernel mode, in some ways, is more useful for attacking, adding debug features, things like that, rather than sort of development, because Sony were actually quite good in implementing a very nice sort of abstracting API to access the kernel and the hardware, so you didn't have to actually mess with hardware registers and things like that. So you can do quite a lot on the PSP. Okay. Ah. Yeah.
Hi. Thank you for the Pandora. It's really helpful. Second, did Sony try to sue you or to stop you somehow?
Not that I've ever been aware of. I've certainly never had any contact with Sony, and as far as I know, anyone else in Prometheus hasn't had any contact with Sony. So, but they try and stop us through software, which in the end failed, so it didn't really matter. Yeah.
So does Sony have any possibility of disabling this in future hardware revisions?
Yes, it's pretty much a hardware and boot code flaw, if they would have to completely revise their hardware to fix it, which unfortunately they've just done a major revision of their hardware. So yes, I think I would have liked to have seen their faces when it got released. So. Okay.
Do you have some Do you have some manual online how to do some homebrew code on the PSP?
If you look at ps2dev.org, there's quite an extensive set of forums on there. Come to the Freenode PSP Dev channel, which is where a lot of us sort of hang out, and we can help people doing it. There is quite a lot of tutorials online. It's a fairly simple thing to implement. It's a fairly simple system to program for, basically. So, yeah, just do a search, and it should be fairly easy to find. So.
Hey, yesterday we had a talk about the Xbox security system, and he mentioned that the crackers or the virus guys, that they helped out very, or not much, but they helped each other out. How was that with the PSP project? Was there also certain of synergies with the virus guys, with the bad guys, or?
Well, in terms of do we have much relationship with the bad guys in the PSP? Or?
Yeah, if they had some breakthrough that you could use, or somehow if they had some, yeah, I don't know, if there was some synergies.
Ideally, we definitely try and stay away from anything relating to the sort of bad guys, because we don't really want to be sort of tainted by that impression. A lot of some of the early sort of deep down kernel work was actually written sort of by the people trying to get Where's loaders running. So some of that sort of information has seeped out into the sort of wider community. But we try our best to keep our tools completely separate from theirs, and they go their way and we go ours.
Hello. What was actually the time frame you used from the first hands-on to the final crack?
For Pandora, or?
Yeah, what you showed now in the presentation, like from the beginning, first hands-on to the final bootload IDL preload or crack.
It was, well, if we go from the initial sort of version 1 hack, that was in April 2005, I think it was, 5 months after it was released. The actual Pandora work was, I think, around 6 months, through various sort of machinations, I think. I don't know. Yeah, about 6 months or so. So it's a fair amount of work. It was actually sort of sat on for quite a long time it was a bit too dangerous to release. But unfortunately, as there was a point on there, someone from our group, which we have no idea who it was, sold it to the Chinese, and the Chinese were basically copying these for people and selling them for large amounts of money. So it kind of forced our hand, and we had to release it. Otherwise, we were going to try and do a 0-day on the PSP Slim to perhaps annoy Sony a bit. Okay. Thank you very much.